How'd that homework go last night? Is it okay?
I struggle.
Struggle a little bit.
I'm just doing this.
Oh, I could tell. I'm walking that way as we turn the lights off.
Get out of here.
Yes. What page did we do last night for homework?
104.
103, 104? Is that what you said? Yay. All right. So let's just see. Let's run through to my daily routine of who owes me what.
Oh. My phone's margin 6.
Yeah. Excuse me. So Liz got you. Sophia Montgomery, you owe me one. So we just talked, right? Good. Maybe. All right. I am all out of pens, my friend. Can someone bum Elizabeth a pen for today? So 103, 104 was homework last time. Let's forward this. I don't know what this is. We'll just move past all that. Okay. What kind of questions did you come across? Dos. All right. Number 2, we have 3 square root 8. Okay. What perfect square is a part of 8? 1 and then 4 as well, right? So we have to realize, okay, if I broke that to 4 times 2, so that means I made that this way. What's the 3 is outside, so if anything comes out with the 3, they can multiply. So what's the square root of 4? 2. So that means I have outside 3 times 2 now. And what do I have left still behind? 2. And then 3 times 2, I think, is 6. So we get 6 square root 2. Right? Cool. What else did you see on last night's assignment? Yeah. 1. So copy. Okay.
I don't understand how you get. Okay, so you break down the 8 and then you do 3 times 2 because 2 is the square root of 4.
Yeah, because it's technically the next step
Which
here.
is not a perfect square.
The next step to this problem is you make it look like that. I haven't really shown that step, but that's how you can split apart radicals. Because remember I said you can multiply inside, inside, and outside, outside. Mm-hmm. We'll break apart inside, inside. And then square root of 4, has to be 2. And then you can multiply those. 1, you said, Oliver?
Yeah.
All right. We have 2 that's already outside, and 75 wants to break down. So what perfect square is part of 75? 25. Good. So I'm going to change this to 3 and 25. Is that okay? Because 3 times 25 is that. So then my next step, I have 2, 25 times 3. Okay, so what's the square root of 25? 5. And that's going to join the 2 outside. Agreed? So I took the square root of 25. I no longer have a square root sign. What's left behind? 3. And then what's that? 10 square root 3. Perfect.
4.
4? Yeah. Ready to move on? Number 4. Root 8 and root 14. Okay? So we can multiply inside, inside together. Does that seem okay? but I don't know if I want to multiply 8 times 14. I think I could maybe put this back underneath the square root because it says I can multiply inside to inside. But I'm not really going to multiply them. I'm just going to write that. Is that okay so far? So let's think about some perfect squares. 8's going to break down to 4 and 2. Do you agree with that? So that's what 8 is. And then 14 breaks down to what times what?
Oh, 7 times 2.
7 times 2, right? Everyone agree with that? So let's figure out our perfect squares. Square root of 4 is 2. Hey, does this also multiply together to give me 4? Does that multiply to give me 4? So what's the square root of 4 again? 2. So another 2 is coming outside. What's still left behind? 7. Hey, what's our answer?
4 square root 7.
4 square root of 7.
Sort of right.
Cool. What else did you come across? Yeah.
16.
Yeah, buddy. Ooh. Oh, okay. It's a word problem. Got a story that's going to be. Can't wait to find out who the main character is. Must be a ladder. A 10-foot ladder is leaning against the wall. Okay. So we have like this wall to some building right here, or a wall or whatever. And then they say you have a 10-foot ladder that's leaning against it. So here's my ladder, and they told us it's 10 feet tall, right? What else do we know? How far is the bottom of the ladder? How far is the bottom of the ladder from the wall? So how far is this? If they told us that this right here was 8 tall. Now, sometimes when you look at that, people are like, how can you have a 10-foot ladder and then you have an 8-foot wall? Well, it's leaning against it. So it's not quite as tall. It tilted over, right? Okay, so let's take this and we'll call this our B value. Is that okay? I could have called it A as well. But I think the Pythagorean Theorem, if I remember correctly, is this, where these are the legs. So that's also known as the shorter sides. That's 2 words. There's 2 words there. Shorter sides. And then this is called the hypotenuse. We'll just call it hip. Okay, hypotenuse of a right triangle is always the longest side. So I know that I have an 8 is my A value, so I'll square that. A B is my unknown, because that's the distance from the base of the wall out. And then my C value is going to be 10, so I get 10 squared. Does that seem okay so far? What's 8 squared?
64.
64. B squared, we don't know yet. Equals 10 squared. 100. Okay, Algebra 1 folk, how do we start solving that? Subtract 64. Good. Subtract 64. So that's going to bring us over to having B squared is equal to 36 because 100 minus 64 is 36. And then really what we're doing here is I want to take the square root of both sides. So if I take the square root of 36, I get 6. Actually, in math, if you take the square root of both sides, you wind up with a plus or minus. Can I have a negative line? No. You know, just because I take 5 feet forward and I go 5 feet back, I don't go negative this way, right? It's 5 feet both ways. So from on the ground, this ladder is 6 feet away. Okay, cool. What else do we see? Yeah.
We do 17 as well.
Yeah. 17. Ooh. This is a small TV. They don't make them this small anymore, I don't think. Okay, so you have this TV set. And here's the screen of the TV set. And they tell us that you have a diagonal of 24 inches. Use 2 little tick marks for inches. And then we know that the width of the TV is 16 inches. So how much would the length be? And it means a TV that should be a right angle most of the time. I haven't seen too many. I see the new TVs that are now kind of curved. They're like curved this way. But it's still like a rectangle. If you flatten it out, it'll still be a rectangle. Okay, so I know Pythagorean Theorem is a squared plus b squared is equal to c squared. So is 24 the hypotenuse? Is it the longest? Yeah, sure is. Because we're not really worried about the whole TV now. We're worried about just this part. We're worried about this triangle right here. Okay? So the hypotenuse is 24 squared. Okay? And then I guess I could call this my a value. Is that okay? So I have a squared plus 16 squared. Okay. So a squared, I don't know. 16 times 16, I believe, is 256. Does that seem okay? 24 times 24 is, I believe, 576. Did anyone do that math? Can you verify that?
Yeah.
Is it right? Good? Okay. Now I'm going to subtract 256 from both sides. That cancels. So I get a squared is equal to, let's subtract 6 minus 6 is 0. That's 2. That's 320. So that means a squared is 320. What I'm going to do at this point is I'm actually going to take the square root of both sides. And technically I should have plus and negative because I took the square root. We're still talking about a length. So now I'm talking about the square root of 320. Well, let's break down 320. Sometimes it's hard to figure out the perfect squares that are part of 320. I mean, we can go on our calculator, go 320 divide by, figure it out. Sometimes it might be easier to say, okay, can I say that 320 is 2 times 180? Is that okay? No, 160. Oh my gosh. I'm sometimes a dingling with you. 160. All right, and then I know that 160 is 2 times 80. Now 80 is 2 times 40. And I know 40 is 2 times 20. And I know 20 is 2 times 10. And I know 10 is 2 times 5. Ooh, okay. Let's see what everything is. I have a 2, a 2, a 2, a 2, a 2, a 2, and a 5. Oh my goodness. So 320 is 2 times 2 times 2 times 2 times 2 times 5. Did I do that right? 1, 2, 3, 4, 5, 6. 1, 2. Okay, good. All right. So if I multiply those two numbers together, I get 4. Square root of 4 is 2. I'll have a 2 outside. That's the same thing, right? Another 2 outside. Same thing. And then root 5 is left behind. What's 2 times 2 times 2?
8.
8. So our a value, simplified, is 8 square root of 5. Yeah.
Okay, so do you have to do that, or?
Yeah, I'd like you to.
Okay,
Yeah,
see,
definitely.
Okay, thank you.
Okay, so let's talk about, we talked about a little bit about yesterday with an exact answer, and mainly an exact answer that we used as a something is your calculators and computers like things to have exact values, or the computer or the phone or your calculator has to have something built in that only allows it to do a certain amount of iterations. That's like running through the program before it stops. If it didn't, the computer doesn't know when to stop. Okay? Other things that exact values are really good for is we've been talking for the past couple years about going to Mars, right?
Yeah, and it might actually.
That's not. Yeah, I think it would be fantastic. I really would. And I love the math and the science behind it, because a few things that people don't realize. When you're in outer space, you have a finite amount of fuel, meaning your fuel could run out. And you don't want to be way out there saying, we're out of gas. Okay, because if you're out there without a gas, you're not going to find yourself at the gas station to fill up. somewhere around the asteroid belt. It doesn't exist. So basically, once we launch a vehicle into outer space, we want it to take off, and it actually circles the planet a few times, getting on a little bit further out each time, and it's building speed. Now, the thing that people don't realize is, if you're on a circle, if I were to take my finger, and if I were to spin around like this, I'm going that speed. If I take my finger and hold it out here, and I go the same speed that I had gone around, whatever the rocket ship at the end of my finger is actually going faster when it's out here than it is here. It's just covering a larger circle. It's covering a larger distance. You remember the circumference of a circle is the distance around a circle. So if you had something that was really close in, so think about this. You have Earth. You take off out of Earth. You come around and you're doing like a spiral. And then eventually on your spiral, you're going to start going so fast that the gravitation of the Earth isn't going to be able to hold on to you any longer. And you actually fly off. Have you ever heard the term a tangent? A tangent is a line that is perpendicular to the radius of a circle. And that's what you want to do. So if you were to launch a rocket, it's not like saying, hey, let's see if we get lucky this time and do this. The people at NASA and the people at Mission Control, or wherever they're at, they put an awful lot of math and science into it before they even ignite those, so they know exactly how long to burn, how fast the ship itself needs to get to. You want it to go in fast enough so as it rotates the Earth, it gets into a larger or further and further out spiral until eventually it breaks away from the gravitation of the Earth. And it's the same thing as when we put people on the moon. You wanted to break the gravitational pull of Earth and allow the gravitational pull of the moon to pull you in. Now, if we go to Mars, I imagine our Mars mission is going to look something like this. And the reason it's going to look something like this is because this would save us fuel. Earth. Seem okay so far? You with me on this story? We have the moon, and we'll call it the moon right here. That rotates around the Earth, right? And about every 28.25 days, we have a full moon. That doesn't mean the moon is now bigger. It's just because of the shadows of the sun and the Earth and the moon, we have full moons versus crescent moons versus new moons. So then, way, way out here, we have Mars. Okay? So what we're going to do is we need a few things to line up for us to make this happen. And they have the math and the science to know exactly where things will be in outer space, which is pretty cool. And it's not just Algebra 1. It goes a little bit further than what this class is. But what we're going to eventually do is, let's say we're down here in Florida. We're going to launch our rocket, and our rocket's going to do this. And it's going to get a little bit further. And then eventually the moon's going to capture us. And we're going to circle around the moon a few times. And it's going to slingshot us to there. So we're going to use the gravity of Earth to break out of. And then we don't have any more fuel that we want to burn until we get to Mars. So then we're going to use the moon to slingshot us around. Now, other large bodies in outer space that have great gravitational features to them is you have something yellow that's in our sky during the day. It's called the sun. So other things they might think about in this characteristic, you have Earth, you have the moon. We'll call the big yellow one the sun. So we might actually do something like this. Let's say Mars happens to be here. So what we might think about doing, and this is going to have a lot of thought that's going to have to take place, because you don't want to go shoot a rocket that hits the sun. I think that would be bad. Right?
Probably.
So I think what they could do is they have a couple of options. We could even do this. Say we slingshot around. Now we're going to go around the sun. We're not going to get close enough to burn anything up. And we're going to go around the sun a couple times, and we're going to allow the sun to slingshot us to Mars. Because the sun is an unbelievable gravitational force, we can actually use the force of gravity on the sun, which is different than the force of gravity on Earth, and it can actually propel us very rapidly to get to Mars. Yeah.
Wouldn't it take a very, very long time to go around the sun?
It could.
By the time
But-
it circles the sun, the people that are on it will be dead.
No. We can get around it. The sun is 93 million miles away as its average distance from Earth.
Doesn't it take like 7 years to get to the moon?
No, it takes us 3 days to get to the moon. Because
Someone told me that.
so
Like,
the moon is 200. I think it's 245,000 miles away from Earth, roughly.
How many miles away is Mars?
Mars is closer than the sun.
So it'd
So
take like a year to
it's
get
probably
to Mars.
50 or 60 million miles away.
So like it would take a couple years to get there.
No, it would take us probably about 90 days.
Oh. Okay.
But it's 90 days utilizing gravitational pulls to slingshot you. Like when you were a kid, your parents ever pick you up and they swing you around like this?
Oh, when you grab
And you
your
feel like
parents-
you're going, whoa!
When
I
you
mean,
grab-
if your parent let you go, you could really launch. If your parent let you go, they can launch. Now, I can tell you, I've done this with my daughters. We'll go to the swimming pool in the summer, and I don't do it with them now because I don't want to throw out my back. Thank you. But I've done this with my daughters. All right, ready? And I've spun them around, and then you launch them, and you want them to go to the direction of the pool because landing on the pavement hurts. But they're like, wow, I really flew far. Right? That's the same exact concept that they want to do with these rockets. And the more exact value you have, this brings us full circle, the more exact value you have, the more precise your calculations. So if you were to say, what's the big difference between having a square root of 2 and 1.412, which just keeps going forever, what's the difference between that? When you start talking about millions of miles, you're talking about getting to Mars, hitting Mars, or missing Mars. That's the problem with not having an exact value versus having an exact value. It's something that a lot of people wouldn't even think about. Yeah.
Is that possible that they go around the sun and just miss Mars completely?
It's very possible, yeah. But that's why you want to have those math calculations. You have the gravitational constants of the celestial bodies. The thing about it is everything in outer space is attracted to everything else in outer space. You have something called the gravitational constant, which is the gravitational constant between all things in our universe. Okay, and Einstein came up with that. That guy with the funny looking hair over there, that's white hair. Okay, so it's pretty cool that we came up with this. We figured it out, but this is how we can actually utilize space flight. I mean, and this is, like going to Mars sounds pretty cool. Going to Mars isn't just someone saying, hey, I'll go. Because you want to make sure that each and every person who is on that spacecraft knows all of the operating systems of that spacecraft. Not like, hey, I'll drive, dude, just chill. No, that person needs to know, how can we do a slight controlled burn, brother? How can we do a slight controlled burn so we can utilize the least amount of fuel if we have to correct something? And that's what we really want to do. We can't build ourselves a rocket ship big enough to fly us. We're not like Star Trek or Star Wars. Okay?
Yeah.
One day, that science hopefully is here. I hope so. I really do. I think it's fantastic. And I love space flight. I love outer space. I love that, a lot of people are like, I don't understand why we're spending this much money to send people to Mars or back to the moon or anything like that. The technologies that we've gained because of space flight allow the things that we use every day. Liz is holding one of them right now. Your cell phones. Your cell phone operating systems were developed because of military use, space flight. And the great thing about space, and I don't know why space has figured this out, no one else can, is a lot of the things with outer space is we are working with other countries to get to this bigger space flight thing. It's not just us going to Mars. It's not just Elon Musk designing the big rocket. Okay? It's not just the guy, Richard Branson, who's designing. These guys are like, hey, we want on board. We want to be involved in this because, one, it's going to make them money, but two, they realize there's beautiful minds all around the world that can make this happen. So when people say, I don't understand why we're doing space flight, it's kind of like, but space flight, you're using people throughout the world. You're not just saying, hey, we want everybody who lives in Texas to do this. Around the world. Meaning you're not talking about borders. And I'm not trying to get on a political stance or anything, but just think about what that could offer the human race. Like, man, we worked collectively as a world to put people at Mars. Wow, we put people at Mars. Wow, what would happen if we worked as a world to kind of figure out other stuff? Okay, and I'm not trying to go politics on you. I'm in no way, shape, or form trying to lead you in that way, but I'm just trying to get you to think. You all are the leaders and the scientists of, my day's past. Okay, I'm not changing careers. I like what I'm doing too much. But I'm trying to plant the little seeds with each and every one of you. Because each and every one of you have that mind that's beautiful. Each and every one of you have that mind that thinks a little bit differently. Is there anything wrong with your mind because it thinks one way and the person next to you thinks a different way? No. We don't want to be the same. If we're all the same, we're like ants. Okay? Oh, I'm going to follow that. No. We're different. That's so cool. You know what else we're probably going to have in outer space? Let's bring somebody who understands music. Well, why do you want someone who understands music? Because you know what? They might understand. I know that the harmonics of this area of the spacecraft is going to be unbelievable, and we can create something beautiful that sounds in here. And then what happens? You get to Mars, you start realizing, look at these crystalline structures here on this planet. What happens if we resonate sound through them? We create sound notes that we've never heard before. Why is that cool? Because everybody loves music. Yes, you like different music than other people. That's okay. But everybody loves it. So you think about what are all the different aspects. How many people do you think, let me ask you this, and it cracked me up. I asked this a couple years ago. I said, how many people do you think would be involved with trying to send somebody to Mars? Do we just take those 12 people who are going to be on there and say, okay, 12, good luck? Oh, there's a lot of people that are here that are saying, man, this is cool. I'm involved with those people. I'm talking about even the guy who is sweeping up the floor at night in the whole, whether it's the laboratory, whether it's in the computer lab, whether it's in mission control. That person has just as much going as the person who is the mind that has figured out the math. That's cool. That's something a lot of people don't think about. There doesn't become yes, you have these fortunate people who are the ones who are actually on the rocket ship. But imagine you sitting there going, you know what? You know that one lever on that ship that made it easier for these people to move in air? They're using my lever every day. Because of my design, they're able to do this. And then you get the person next to you. Yeah, but you know what? Because I was able to figure out the trajectory of the slingshot around the sun, we saved 5 days travel time. Whoa, that's pretty cool. And then you get the guy going, yeah, but you know what? Because I'm cleaning your area that you're in, you're able to get into your area comfortably and continue to allow these processes to take place. So from the custodian all the way to the person who's on the ship and everybody in between. That's a big team effort. Is there money in this? Yeah. Okay? Now, I'm not saying the custodian's going to be making the exact same wage that the guy who has a PhD in math that we haven't even discovered yet has. But each and every person along that way. The person who was at the metal plant who designed the alloy that was light enough and strong enough to withstand these pressures has just as much into it as all the people at the plant. The person who designed the little tubing so people could go potty in space. And you want to know what you have to do with the potty in space? Nope. The urine you run electricity through, and that becomes the water you drink.
Oh, so nice.
Yeah.
That is so nice to know.
What happens to your waste at the other end? Well, they realize that some consumables might not do well, so we are going to run a little bit of electricity through it so it becomes sanitary. And then we're going to use it as the soil and the plants on our ship that will grow our food.
Will it smell?
Sophia said eat.
Oh, I wouldn't eat it, no. So then, on the other end, what should we do to keep the soil and everything on board hydrated? Well, we should probably have some sort of fish apparatus on board where there's fish that are eating certain wastes, that are excreting their waste, that then turn into other soils that increase the nitrogen output because of, there's an unbelievable amount of stuff that takes place with this. It's not just a small thing. Okay? It's not just saying, hey, we're going to strap you to a tin can and say, good luck. There's a lot that goes with it. Will you be a part of this? I don't know. Will you be sitting at home at some point watching the news going, that's pretty cool? Because you know what? Anytime we're going to do a news report on space, I want to watch that news report. I don't want to watch any other news reports. But I like hearing the science that we're doing. Okay, is this all developed and done? No, there's stuff that's having to be invented to work through a problem. Okay, the engineer who develops that has to find people to fabricate that. People that fabricate that there has to be people that are finding the metals and polymers to make that. It's big. So we go send 10 people to Mars. I would say conservatively 20,000 people are employed because of it. Conservatively. I bet you the number's bigger than that. Is that a lot of people to employ? Yeah. There are 20,000 jobs waiting for you to find that you haven't even discovered yet. Those jobs haven't even been created yet for you to go to Mars or for someone to go to Mars. I think the future is looking pretty darn good. I don't know about y'all, but it all comes back to, can you get an exact answer? Can you get an exact answer versus it's okay if we round off? That's the big difference. And I just spent 20 plus minutes giving you a little perspective of why is that number big? I don't know about y'all, but I want to see us hit Mars. I think that's going to be pretty cool. I will tell you, y'all think you're glued to your phones right now? Just imagine finding out, hey, today is the day we're going to get to Mars. What time? It's going to be at 12:42. I'm busting out my phone. I'm watching that live feed. Oh, this is cool. This is cool. This is cool. Okay? 1969, when we stepped onto the moon. There was over 1 billion people watching TV around the world, watching us step onto the moon. And you're like, yeah, but so what? There's like almost 8 billion people on the planet. Yeah, in 1960, there was 3 billion. So 1/3 of the people on the planet were watching. How many people will be watching when we do this?
Probably over a billion.
A lot. Why don't I lecture on this tomorrow? Why don't you use tonight to make sure that your homework is good? If you feel your homework is good, you can put it in the folder. If you have anything else to hand it in. Yeah, but